Good morning. Okay, I'm just going to give it a couple more minutes. Okay, Valeria, if you have a question during any of this, just unmute yourself and ask, because I'm not really following the chat box, okay? All right, so, okay, good. Before I even start this, I want to just remind everybody, this constants and equations sheet is uploaded. It's the front page is just all like 3 columns of equations, and the back side is all the conversions. If you have not already printed this out, I highly recommend you do so. This is going to be kind of your lifeline on your tests, on your mini quizzes. Almost every single equation you could ever need for this semester is on that sheet. And in fact, if you have the hardcover textbook, not the e-text, but just, or any actual tangible textbook, it's the back cover of that textbook. So highly recommend printing that out. And I deface all my stuff and I write little notes all over it. Highly recommend doing that. All right, so we're going to continue with chapter 12. If you missed it, I did put up the first part. I was able to get a lecture done yesterday. So I put that first part up. We're going to go over the second part, and then we're going to introduce intermolecular forces for chapter 13. So, and actually, hang on. Let me make sure I pulled up the right stuff. Seriously? All right. Yes, I did. Okay. I just had to make sure I pulled up the right one. Okay. So when we talk about crystalline solids, we've already talked about how structure is so critically important to the behavior of compounds. Not only does the structure matter, but in the next chapter, we're going to really dive into how that structure affects things. You've seen it already in Gen Chem 1 with Lewis structures. And what you've seen is that when we get polar bonds and all that kind of stuff, it really affects all that. Now, I'm going to reintroduce again intermolecular forces just to kind of tie back in, and we'll go from there. So when we talk about these crystalline solids, we're going to be able to classify them in different ways. So for example, if you have a crystalline solid, which can be molecular or ionic, you can also have atomic solids. And these would be things like solid gold, solid aluminum, quartz, all of those kind of things. So when we talk about molecular solids, we have pretty low melting points. And if you remember, melting points are affected by those intermolecular forces that we touched on in Gen Chem 1. So with ionic solids, if you remember, that's a metal and a nonmetal, and the moleculars are all nonmetals. And again, the atomic would be just individual atomic elements, something like solid gold. Okay, so with these ionic solids, we're going to see high melting points. But for the atomic solids, it's a little bit different. When we talked about intermolecular forces in Gen Chem 1, we briefly touched on dipole-dipole, London dispersion, hydrogen bonding, and then metallic bonding. And we see a lot of that happening with these just elements that are in and of their own right bonded to each other. So solid xenon, if you recall, xenon is a noble gas. So when I have a bunch of solid xenons together, they're going to have pretty low melting points. Gold is the example they give for metallic. The melting points are variable because it depends on what metal it is. Pure substances is what we're looking at here. Okay, quartz, that's going to be your network covalent. And in fact, I want to show you guys this. Give me 1 second. Let me pull it up. Okay. All right, so we're going to be looking at this picture. Can you guys tell me if that's big enough? You guys can see this okay? Awesome. Again, Liliana, I'm not really paying too much attention to the chat box right now, so if you need to say something, just unmute yourself and say it. Okay, so if you remember when we talked about carbon could be in two forms. You saw that all the time. Carbon was either in the graphite format, and that's where we see things like a lead to a mechanical pencil or a number 2 pencil. But then also under extreme pressure, that's where we get diamonds from. And if you note the structure of graphite, which is right here, it's very geometrically linear, right? We have all these carbon atoms just kind of stacked, if you will, kind of like, I think of them like Lincoln logs. But when you get to diamonds, we have what's called a network covalent structure, where it's a very different structure from the graphite. Honestly, in our kind of mantra of chemistry is everywhere, you're eating it, breathing it, sleeping it, like everything involves chemistry, to include marketing tools. Well, having the career of a gemologist means you're kind of exploiting, if you will, the molecular structure of diamonds for the cut and the clarity. Like we all know that there's all sorts of different cuts of stones. I'm going to stick to diamonds. Round cut, cushion cut, emerald cut. And depending on how they're all cut, you get lots of sparklies, or you get more like of a solid look, or maybe a solid look in the middle and sparklies on the side. And just it's all has to do with the way it's cut. In fact, back in the before the Depression, I want to say like turn of the century, 1910, 1920, if give or take, the most popular way to cut a raw diamond was what they call mine cut diamonds. So they would mine these diamonds and they would cut them in a certain way so that they were round but didn't really look round. The best example of that is if you've ever seen an antique diamond ring, like maybe your grandma's or great grandma's, where it has kind of this bubble look to it, but still very sparkly. that was manipulating the structure of this diamond. So the structure of the diamond versus the graphite clearly makes them very different in their utility and what happens. And that's going to be true for almost everything we look at when it comes to structure. Okay, so this is, again, just kind of summarizing that chart you just saw. You have the molecular solids, the ionic solids, the atomic solids. I'm not going to go through this again because I just went through that chart. This is just in words what the flow chart was. I have a tendency to like this flow chart better because you can better see the separation and how their structures work. So when we talk about these, we're going to talk about specifically lattice sites. We talk about those in terms of molecules. Again, remember, molecules are all nonmetals. They're compounds that are composed of all nonmetals. So these are your examples: carbon dioxide, water, table sugar, and we're going to have intermolecular attractive forces. They could be dispersion, dipole-dipole, hydrogen bonding. It just depends on what they are and what their structure is like. So if you remember from biology, you had bilipids, if you remember that, right? Where you had a polar head and a non-polar tail. Well, your polar head usually consisted of a carboxyl group, and then your non-polar tail was some sort of hydrocarbon. Now, the length of that tail, which is all non-polar, versus the strength of this polar head would determine the overall behavior of those fatty acids. And if you remember from your biology courses, you often saw where they were in sets of 3, right? Where you had a couple of things going on here. I'm really bad at drawing biology stuff, y'all. Sorry. We're going to pretend all those points are carbons and they're beautiful. Okay, so when I have a very short chain like this is my non-polar end, compared to this hugely polar head, this overall will behave with a stronger partial negative on the polar end than the partial positive on the non-polar end. But as soon as I make these tails really long, some of the fatty acids you studied were up to 26 to 28 to 30, carbon chains. If I were to make these super long, then the non-polar tails will then overtake the ability of the polar head. But the way all of that works, it kind of balances out. So lattice sites are occupied by ions. If you remember when we watched that short video with all the 3-dimensional pictures of the unit cells, you saw that, we were talking about what positively charged metals were there and what negatively charged non-metals were present, and how they kind of lock and key fit into, again, I think of Lincoln logs, into a geometric pattern of structure. And so we pretty much reserve the lattice sites with ions to the ionic solids. Okay, these are ionic. They're not polar, they're not non-polar. They have a full charge in and of their own right. When the metal becomes an ion and the non-metal becomes an ion, they get a full-on positive, full-on negative, and we refer to that as ionic. And it's the attraction is because of the oppositely charged ions. So that coordination number, it accounts for the cation and anion interactions. So if you remember, the cation is your positively charged metal, and your anion is your negatively charged nonmetal. And so our coordination number directly has to do with that positive and negative attraction of the metal and the nonmetal. The higher the coordination number, the more stable the solid. That should make sense, because if I have a higher coordination number, then I have a higher number of cations and anions attracted to each other. And that doesn't necessarily mean just between one or two. So for example, if I have sodium ions and chloride ions, and I have more than one of them, right? Yes, the chloride ions are going to repel each other, and the sodium ions will repel each other. But these will be attracted, those will be attracted, and those will be attracted. So the higher the coordination number, the more stable it is, because the more attraction there is. When there's more attraction, we have lower potential energy. Remember, energy is key to stability. So the lower the energy, the more stable something is. So that means the higher the coordination number, the more interaction between the cations and anions, which lowers the energy, therefore making it more stable. The coordination number also, this is an important part, or an important note, the coordination number depends on the size of the cations and anions to maintain charge balance. This is an important thing. Charge balance, it's literally in what it says. How balanced are the charges? How even Stevens are they? So anions, we know, are larger than the cations. So the number of the anions, it's really going to be, it's going to have a limit because of the cations. Their sizes impede other things. So you might be able to get super close, but still there's a distance because one is much larger than the other. This last bullet right here, that think about it in terms of if you had a marble and a kickball versus all marbles. Okay, so you know what? I don't want to use marbles. I want to use those little decorative beads that you can like buy at Michael's that you put in a vase to make it all pretty. Those are generally the same size, but not identical in size, and that's why I don't want to use marbles. So if I had one of those decorative beads and a kickball, clearly I can only put so many of the beads and the kickballs together in order that they all kind of sink into each other appropriately. But if I have just a bag full of beads, I can compact them much more easily and much more effectively, and there's going to be way more there. So the more similar in size these ions are, the higher the coordination number. Higher the coordination number, more stable it is. So here's an example you should go through and see if you can figure it out, or understand why. You know, classifying each. You got, this is again throwback to Gen Chem 1. Remembering that, you know, moleculars are all nonmetals, atomics, what they are, ionics are the metals and the nonmetals, etc. So there's not going to be a ton of math involved with these, the cell units, but you do need to understand the generic part of it. So for example, if there's a coordination number of 8, what that means is I'm going to have one, oh, I can't use green on this one. 1, 2, 3, 4, 5, 6, 7, 8. Okay. That is when, if you remember the slicing from the video, that means each one of these is going to be 1/8 of a chloride ion. Okay. Now, I have one cesium in the middle. So when we're looking at what's happening here, and the cubic hole, the hole in the center there, but there's not because there's a cesium. What you can do is you can say, okay, based on the coordination number, how can I predict what is the formula going to be? So in this case, if we have 8 as a coordination number for the chloride ions, and 1/8 of them is there, 8 times 1/8 is 1, right? Just throw back to math. 8/8 is 1. So my cesium, which there's 1 there, here it is, to chloride ions is simply 1-to-1, so you can predict the formula to be CsCl. You can also do this with much larger, more complex ionic solids. So if you look, we have a coordination number of 6, but we have chloride ions all up in the corners. And then we have the sodium ions, where the sodium are the purple and the green, no, the chlorides are the, I think I just said that. The chlorides are the purple and the green are the sodiums. But you get these octahedral holes. So this is a much larger, much more complex structure. So we would expect to see this if I had maybe a whole rock salt, like you know, those chunks of rock salt, maybe what they throw down in the ice when it's icy to, you know, keep everything from freezing up on the sidewalks and the streets. And that is just sodium chloride. So you can take into account all of the different things where we have 1/4 times 12 of the, you know, of the sodiums, and then you have the carbon, or I'm sorry, the center. Here's your center right there. And then you have, you know, all of these where they're face-centered. Okay, you can go through and do this math. I'm not going to expect you to do that. That's just an example here of a more complicated structure where you can, with the face-centered, you know, just mathematically figure out what the formula should be just based on a structure. You can do it with this one also. Again, these are just generic examples. I think if I put one on the exam, it'll be body-centered, but these are much more complicated face-centered cubic arrangements. And I don't like to ask test questions on these because they're really, really hard to see, especially on many of the tests when you print them out, or you know, you throw up a picture embedded into a question. They're often black and white, so they're just really difficult to see. So if you're going to see something like this, it's more than likely going to be the body-centered or simple, but not face-centered. Okay, we already talked about the graphite structure versus a diamond. If I remembered the structure was in here, I would have done it. But this is cool. A lot of people don't get to see this. This is a raw diamond, an uncut diamond. It almost looks like a ball of aluminum foil. They're really cool when you see before they're cut. But some of the properties of a diamond is because of this network structure. So it's just really cool to see all that. So we know that, you know, diamonds have a very high melting point. They're very rigid. They're very hard. In fact, we use diamonds as tips and tools, like for tile cutting. Diamonds can be tipped on the blades of circular saws. to cut very, very hard stone like granite or marble. Well, marble's pretty soft, but granite, for example, like kitchen counters, a lot of those tools they use to do all those kitchen counters are diamond tipped because they're so very hard. They're great insulators and thermal conductors, and they're pretty non-reactive. So when we look at diamonds and we look at what they're good for, as opposed to being pretty on our fingers and ears and necks, they also serve a very, very good purpose. With such high a melting point and being so non-reactive, they're great for things like insulation, conductors, and tools, aside from pretty jewelry. This is just an interesting, it's the buckeye ball. If you know anything about Ohio, you know what a buckeye ball is. But this whole structure is just an interesting structure used to create this artwork. And I honestly, I've never been able to say this name. I butcher it every time. Buckminster Fullerene, I don't know. But the guy who created this, 20th century engineer, which means he was, I'm going to say like mid 1950s. It was after World War II, not quite DNA known yet. So sometime between like the 50s and the late 70s. That was his peak. He wanted to use these based on actual structures of actual elements. That's what he wanted to base the engineering on of buildings that they were constructing, because he figured if we model in our engineering the natural in nature complicated structures of compounds, they would be more stable. And in many cases, that's true. In fact, many of the ways in the Asian countries where they design earthquake-proof, and now they're starting, or I guess they have been starting to do that in California, earthquake-proof sky rises, they're modeling that structure. And it just becomes very interesting to read about. Silicates and quartz, you don't really need to worry about that. You do enough of that in biology. That's the end for this chapter, for part what are we at? Part 2 of chapter 12. I am today, later in this afternoon, I'm going to record. We're going to introduce or reintroduce intermolecular forces and liquids and solids, or liquids and intermolecular forces. I'm going to start that. I want them separated out from this lecture so we can keep straight all the chapters. If you have not gone back yet and watched part 1 of chapter 12, then go ahead and do so. I realize it says chapter 11. I need to fix that. This is from a different book, a different version of this book. So it is still chapter 13, but it's just a different version. It's a different edition. So I will do that later on this afternoon. It should be up no later than like 5 o'clock. So if you have any questions, now's the time to ask.